Thank you everybody for coming. Please drop your questions in the Q&A feature, the Q&A box. There's 5 people who have already written some questions in, which is wonderful. We'll be monitoring them as we go and pitching them to Matt and Graham. Thanks for an amazing year of space time. This will be our last Hangout for the year, and coming into next year, we've got a lot more episodes. And Karina says it's the Q&A panel. Yes, please put it into the Q&A panel. So let's get started. Okay, first one from Karina. I've started uni classes and I'm looking to major in astrophysics. I was wondering what you guys thought about the state of physics as a career path. What are your guys' thoughts about a BSc in astrophysics in the private sector? I hear the academic sector isn't very healthy. I wanted to learn astrophysics so that I could explore dark matter, but it seems like that's a distant dream.
Yeah. Well, it sounds like you're very realistic about it, which is good. You know, I think it's a challenging market for sure. Academic, like there are so many more grad students than there are postdocs, and so many more postdocs than there are professors. That said, you know, last time I looked at the numbers on this, the employment rate of physics grads was extremely good. Okay, so physics grads do get their jobs, and that includes astrophysics. People with physics and astrophysics degrees tend to be headhunted. You know, they can be headhunted, but it looks good. You know, there's this crazy perception that you're smart if you've got a PhD in one of these things, and we hope to really keep that illusion going, which is really what this show is about. But so, you know, I would say follow your curiosity, but you know, also keep your eyes open and your mind broad about potential futures. And I also think this is something that Graham can speak to.
Yeah, Graham, who has a PhD in quantum physics, but now you do work in the private sector, right, Graham?
I do. I sold out, sort of. But yeah, so obviously I second everything Matt said, especially about sort of the numbers in academia. But yeah, definitely there's, yeah, I'd say it's worth doing. If I were to condense my answer, it would be just sort of have a backup plan in some sense. Like you can say, you know, success or the goal is potentially research, but if I fall short of that, here are the things that I can do with what I got along the way. And I think if you do that, then, and there's definitely options there, as Matt said, then, you know, it might be disappointing if it turns out that your market is too crazy to end up in research or something like that, or in the field that you wanted, or in the location that you wanted. But you'll be making use of all that stuff. And definitely, as Matt said, you know, people with physics undergrads and graduate degrees are definitely sought after. I guess the one bit of side advice I would give is, and this would probably come up doing astrophysics research anyway, and Matt can probably chime in on this as well, is one of the things that makes people like hiring physics grads is, in addition to maths and problem solving and critical thinking, all that sort of stuff, is programming. So if you have the opportunity to take, you know, go in programming, that's a super useful skill, both in just modern research. Like huge amounts of modern physics research is computational these days, and you sort of have to dip your toes into that at some level. But in industry, that's hugely valuable, and it's also super fun and interesting. Like it shouldn't be seen as this kind of chore. I think it's pretty amazing in its own right.
Yeah, and there are some really good feedback in the chat here. Colin has some statistics. Forbes magazine ranked 400 occupations. Mathematicians were number 1, physicists number 5 or 6 out of the top 10 careers. And I'm not sure, is this for earnings or what? Or some kind of different set of criteria for top career, but presumably they're good. But they involve, but I think what is it? 4 of the top 10 involved advanced math. And then Oliver says that physics as a degree just floats through the recruitment where Oliver works, which is a major finance house, because these people are smart, thorough, and logical. Thank you, Oliver. We try character traits which will always be in demand, and yeah, so that's the sense. But that said, if you're going through a physics degree, also, keep your mind, open to specific things that you would like to do otherwise as well. So you can kind of semi-direct your path as you go forward, and tailor your skills as you move along, whether it's programming or statistics or whatever, depending on what you're interested in, or technology, the tech sector. Okay, become an entrepreneur afterwards, or
But a lot
so
of
many things.
people, I feel, enter, physics and physics because they really do want to study one element of the science. Like, for example, Karina says she wanted to study dark matter. And what kind of advice would you give to somebody if they really do have a targeted dream like that? How do they stay on track during undergrad and grad so that they can try to do their best to end up teaching and researching in that particular niche field?
Oh, well, to that I'd say, again, keep your mind open, because dark matter is very cool, and you may end up being principally interested in dark matter later on. But as you become more exposed to different areas, your curiosity is going to be piqued by all sorts of things, and your passion may well shift to other fields. You may be, massively inspired by a professor, or, just have some opportunity to enter some really cool project that has huge potential. So don't be too rigid. With something like dark matter, you'll always find people who want to do it. We just did a bunch of interviews for a job that I'm looking for a postdoc, actually, in gravitational lensing and quasars, and a huge fraction, like maybe a third or a half of the applicants were all about dark matter, which is fine, because I also know that they're going to be interested in the other things that we want to do. But yeah, so there are hot fields, and dark matter is a hot field right now. If the person who gets it's going to get a Nobel Prize, who figures out what it is, but it's not the only hot field. You're going to find areas that people haven't even thought of yet, amazing questions that you can pursue, that you might be more on the forefront as opposed to one of the thousands.
So Karina says that she's always followed her curiosity and passions. So wherever she ends up, she won't be disappointed, as long as she doesn't end up back where she started. And I can guarantee you that if you get a PhD in astrophysics, you'll find some kind of cool job. And Colin says, you never end up where you started. Indeed, that is true.
There are closed time-like loops somewhere, probably.
So by the way, guys, I need to, just because it's eerily topical right now, the episode that I'm writing, that I was writing right to the minute before I started this call, and we'll go back to writing afterwards, and we'll probably get up at 4 a.m. to finish writing to shoot tomorrow morning, is an episode on paradoxes in relativity, inspired by a question that Hank here asked. And the spoiler is that you never end up back where you started. But Hank, do you want to share the question?
Okay, the question was, and it's one that I've had for a long time, is that, at one point people thought the universe was closed, that it was basically like the three-dimensional analogy would be a sphere, and if you go far enough in one direction, you come back to where you started. So I was I had just been introduced to special relativity, and I thought, okay, let's say you're traveling in a spaceship and you have enough fuel and a matter antimatter engine. Let's say you go so fast that your spaceship approaches the size of the universe. Does the tail of the ship eventually reach the nose, or the nose reach the tail? And if so, does it, if it damages the ship, let's say it damages the matter antimatter containment field and the ship blows up. Well, that creates a paradox, because to a stationary, an outside observer, the ship would remain intact. It would be contracted. The universe would be its normal size, quote normal size. But on the ship, it's a universe that contracts to and approaches zero as you approach the speed of light. So that was my question.
And
what really happens? Does the ship eventually curve in upon itself in a closed universe?
so, like I said, the answer is in a sense that you never end up back where you started. And I'm not going to tell the answer because I want you guys to watch this episode where we'll have good graphics to accompany the answer. But I feel like this should be a quiz. Does anyone think they know what the answer is? Does a ship moving at very close to the speed of light length contract the universe so that it smashes into itself, or doesn't it? I guess is the question. What's the solution to this paradox? And if anyone has an idea, maybe we can take a poll. I just spent the whole semester teaching online, and so I'm used to like throwing up polls to quiz the students at any instant on Zoom. We don't need to do that directly, but I'm just curious what you guys come up with. Okay, so first up.
Patrick says, to hit your own ass, the universe needs to be closed.
Yeah. Astoris says, is it similar to the garage ladder paradox? Indeed it is. It's very closely related to the ladder paradox. And the version I know is that if you take a ladder that, if you have I have the barn, ladder and barn. If you take a ladder that's longer than a barn and you pass it through the barn, then someone who's stationary relative to the barn will always see at least one end of the ladder poking out of the barn. But if that ladder is passed through the barn at close to the speed of light, then someone stationary relative to the barn will see the ladder length contract so that at some point it's entirely enclosed by the barn. Okay. But someone traveling with the ladder who's traveling at close to the speed of light will see the barn length contract. And so the ladder gets even longer and so does not fit in the barn. So who's right? Does the ladder fit in the barn or doesn't it? Well, if the barn becomes the universe, then so the answer is that we need to consider the relativity of simultaneity. Please watch the episode for details on that, which is that the observers have a different sense of the timing of when the front and the rear of the ladder cross the thresholds of the barn, and account those crossings as simultaneous in one sense or as happening in a different order in the other sense. Okay, and that's where the solution comes from, and I'll explain that in the video that we make. But to extend that to the whole universe is really tricky, because instead of having one barn door, you have a barn where the doors map to each other, Pac-Man style. Okay, and so it took me a while to get my head around what actually happens. Okay, the ladder's passing through the barn, but then its head's going to come out this end, and it's kind of a mind bender, but there is a clear answer, and you'll have to wait. Do we have any other answers? I just got to the first response here.
I was going to give a cop-out answer, which is if we're talking about the universe changing size, it's it's beyond the scope of special relativity. So I reject the premise.
Yeah, but then we can just invent this barn that has these doors that map, right? And the barn
Oh,
can
you
be
topologically
spatially.
glue all these barns together.
Yeah, exactly. Yeah, we can have a topologically compact barn.
Yeah, it's a great band
a
name.
toroidal barn or something.
Mobius barn.
Did you say Mobius barn?
A Mobius barn. Similar.
David Johnston asks, even with all of energy present during the time of the Big Bang, the universe went through a period of hyperexpansion. How confident are we that the expansion rate of the universe is affected by gravity? Could gravity just curve space-time without having an effect on its expansion rate? Could dark energy be something that solely influences that rate and otherwise does not interact with the contents of the universe? I.e., it won't have a field theory explanation. It's the second question there.
So can you repost that? I think when I rejoined, it disappeared from my list.
Yeah, I'll put it in
I
the...
definitely need to read that again.
Oh, you can't copy paste from the Q&A. Even with all the energy present during the time of the Big Bang, the universe went through a period of hyperexpansion. How confident are we that the expansion rate of the universe is affected by gravity? Could gravity just curve space-time without having an effect on its expansion rate? Could dark energy be something that solely influences that rate and otherwise does not interact with the contents of the universe?
Well, I mean, the expansion rate of the universe is described by and was originally predicted by the Friedman equations, and like a year after Einstein's theory came out, and the Friedman equations basically take the Einstein field equations and simplify them under the sort of symmetries and assumptions you can make when you're talking about the whole universe, and they give you an expansion rate which depends on these properties, and that includes the mass of the universe. And I think mass would have to be something very different to what we think of it, to how we think of it for it to be otherwise. Einstein, looked at the Friedman equations and saw that the mass in the universe must affect the expansion rate, and in fact, a universe that has any mass must either expand or contract. It couldn't be static. So mass as it is defined in general relativity in the Einstein field equations affects the expansion rate, and I don't know if there's a way around that. And then, of course, dark energy, which causes the accelerating expansion, was in addition to those Friedman equations that Einstein put in to try to circumvent, to try to balance the effect of mass to give a static universe. So let me see, how close did I get to answering this?
He follows up in the chat and says, does gravity really negate space expansion effects at the local galactic cluster level?
Oh. So I think the answer is it does completely. I think. Graham, what do you think?
Yeah, I mean, yeah, so I sort of understood this question as saying, is expansion caused by dark energy, say, or inflation, and curvature caused by gravity or negative gravity, if we negative mass, if we had that, sort of acting on the same thing? And I sort of agree with your answer, which is, as far as we can tell, yes, because when we look at these field equations, like the Friedman equations, they're acting on sort of like the same stuff, like they have opposite effects, like the gravity from mass definitely counteracts the expansion. As for and when you do the calculation of that at the local sort of cluster level with the latest version of the Hubble constants and all of this sort of stuff, Hubble parameter, I should say, yeah, it does negate it. Although I guess I don't know how you would necessarily measure that directly. I don't know that you can. I don't know that you can really do an observation to say if that's. I guess we could look at other clusters far away and see that they're somehow still clustered together versus stuff that's expanded in between. I don't know.
I mean, the only way would be to. So the issue is that dark energy is an incredibly weak effect that only become significant when you add up vast tracts of space between the galaxies, between the clusters of galaxies, so that inside the Milky Way, it's negligible. You can explain the rotation of the Milky Way, the gravitational kinematics of the Milky Way just with gravity, and you don't need to inject dark energy. So you need to find a system where the effect of gravity and dark energy were roughly equivalent within I guess a couple of orders of magnitude. You need to find something that's so loosely gravitationally bound, or just outside being gravitationally bound, for these two to be comparable effects. So you're kind of looking at maybe the like two filaments of galaxies between the clusters, and seeing their interaction with each other. But the problem is you can't really measure the motion of those objects, of those stars or whatever, with anywhere close to the sort of precision you need over a sufficient time scale to measure what I assume must be an insanely subtle effect. Yeah.
Yeah, I think that's a good point, in the sense that if the expansion is an observed fact from Hubble observations and things like that, and the acceleration is an observable fact, or at least it should be if it got a Nobel Prize. And but then your point is I think is a good one about, well, on the local scale or at the cluster scale, we absolutely don't need that term in our equations to get accurate descriptions of what we observe, therefore. And that, coupled with the fact that when we write down these equations that we know work pretty well, we see this counteractive effect. So I think that's pretty strong evidence to say, that it does what we think it does.
Yeah.
Patrick Gilmore, Pat, who always joins these chats and always has great questions, asks, quantum entanglement question. Assume you have two entangled photons. I know if you look at photon 1 and it has an up spin, then photon 2 has down. But how do we not know photon 1 always had up spin and it was not forcing photon 2 to have down spin just by looking at photon 1?
Yeah, the answer is to look at the statistical test designed by a guy called John Bell, an Irish physicist. So there's this thing called the Bell test, which is a statistical test which you can do if you have a number of entangled particles that starts out, that are correlated, but due to the fact that their states are entangled. This is a hugely complicated thing to get into. We have an episode somewhere, but in short, the idea is that in the spooky version of entanglement, it's not just that two states are correlated. Like if one spin is up, the other is down. Okay. They say the two particles created in the same reaction, they must have these correlated states. All right, big deal. Okay, so it's not spooky action at a distance. It's just information. You gain information about this particle if you learn it about this particle. But the weirdness comes about when you realize that your measurement of one particle can affect the state of the other particle. Okay, in order to determine the direction of the spin, you need to choose an orientation for your measurements. Okay, if you measure in the vertical direction, you'll get up or down, and the distant particle will reflect that in the opposite way, up, down, down, up. Okay, but if you choose your measurement basis for the first particle to be horizontal, then you're going to measure left or right. Okay, you have to measure left or right. And the crazy thing is that then the opposite particle will always have the opposite spin, left, right, right, left. Now, if it was the case that these two particles had opposite spin in a different direction when created, definitely up and definitely down, and then choosing you know, then naturally choosing the up-down orientation for this one would give you up here. Choosing the up-down orientation here would give you down here. Okay, that's not mysterious. But the weird thing is that if you choose the horizontal orientation, quantum mechanics says that, all right, well, because this is up, then it's going to be 50-50. Okay, it's going to be 50-50 left, 50-50 right. All right, which would mean that if we had this sort of classical correlation, okay, this one was up, this one was down, then if you do the horizontal orientation on this side, because this one's down, it should be 50-50 in both directions. And so you should end up with kind of uncorrelated spins. Okay, so if you start out with definite spin directions, separate them, and then do what we'll call an orthogonal basis and make the measurement, then both should be 50-50 independently of each other. But that's not the case. The case is if you choose horizontal spin direct measurements and you get left here, you'll always get right here. Okay, and so the thing that's that appears to be translated is the oppositeness of the spin. They just have opposite spin, but without the specific direction defined, which makes it feel like the choice of measurement basis defines the spin in one place, defines the spin in the other place in a way that you know, could allow communication faster than light, because this is, you know, feels like a type of information. Okay, so how do we know that this is the case? Well, this is where the idea of the Bell test comes in, there's this statistic which is called the Bell inequality, which says that it's basically a way of doing a statistical test about how these separated quantum states are correlated, and you can Google that. We have an episode on it, but this is something that's been tested again and again, and nothing has ever failed the test. Okay, it appears that the quantum weirdness persists. Okay, Graham, please correct me or add.
No, that was pretty much the perfect answer. I think it's really important to reiterate a couple. Yeah, so yeah, the key thing there is that there's this difference between like classical and quantum probability. So if you only consider that like two-dimensional up-down thing, you don't get this picture. Like, it really, the crucial aspect is this randomness of the measurement in the orthogonal directions. And without that, you don't get this kind of weird behavior. So yeah, no, I have nothing to add. That pretty much covers it.
Okay,
I mean,
yeah.
I don't know how you, there's other tests you have to do to disprove kind of hidden variable theories, but that's I guess a different thing.
Yeah.
Like you have to show that the actual level of correlation you would get is yeah, statistically different to what you get in the full quantum picture, and that full quantum picture is what corresponds to what you do when you do what you get when you do the measurement. And so that's how you can sort of show that you can't explain this with a hidden variable.
Yeah, and I also feel it's important to add that that it's been improved pretty conclusively that there is no way to communicate faster than light this way. All you can do is produce this set of correlated quantum states at a distance that can only be verified when you bring those quantum states together slower than the speed of light to compare the results. Okay, and so the universe conspires to stop you actually communicating this way.
Yeah, you can't send any actual information other than, you know, random. You don't get anything better than random until you do that comparison.
Tom asks a very interesting question. Is it possible that gravity is just energy flowing into the future? When energy/mass collect, they cause time dilation, and in turn, space-time starts to move in that direction. For example, energy tells time how to flow, and time tells energy where to go. Remember, acceleration is measured in m/s², and I believe time dilation s²/m. This might be tested by taking a large body and checking its time dilation versus gravitational pull at different heights above the Earth. You see that one in the Q&A, Matt?
Yeah, I'm reading it now. I mean, I can say that the various chunks of this are correct. Energy flowing into the future is kind of, mass is in a sense that. Yeah, this is one that I don't feel comfortable digging into right now because there's a lot going on in this question. So, Tom, if you're comfortable, I can think about this a bit harder and not make an idiot of myself right now. But Graham, do you feel otherwise?
Not hugely. I'd have to think about it a bit as well. I mean, I think, yeah, yeah, same. I mean, I have to think about what it means to have space-time move in a particular direction caused by time dilation. But I agree about your point about mass. You have static mass, and that just has a world line, and that's moving energy from the past into the future as it just sort of sits there. So, in some sense,
I mean, this is obviously connected to the idea of the gravity being dominated by the fact that clocks tick at different rates within a gravitational field, and that kind of gives us the force of gravity. That, Tom, that I agree with. That's the case. But
yeah, it seems just sort of like a slight recasting of the way we think about gravity in terms of what space-time now, in some sense.
Yeah. Okay. All right. We're going to table that one and scratch our heads on it. What else we got? Brody, you had a Brody, you had a question in the chat. Do you want to say it, or shall I welcome Brody, by the way?
Yeah, thanks. Sorry for being late. Yeah, my question is, do you have any thoughts regarding Jeremy England's idea of dissipation-driven adaptive organization, both on the level of what it seems to us to be, sorry, I totally misworded this, up on the level of life, like on our level, all the way up to the level of astrophysical objects. One of its core ideas, I think, is that replication is a form of energy dissipation. To quote England, you start with a random clump of atoms, and if you shine light on it for long enough, it should not be so surprising you get a plant.
Yeah. So we did an episode, believe it or not. I guess we've done a few episodes by now. I mean, this is awesome stuff. So, it's like you've definitely hit on a very cool concept. So the episode is called The Physics of Life. And it was the one we did in collaboration with Eons and It's Okay to Be Smart. 3 episodes on the origin of life. And so, yeah, the idea is kind of a counter to this notion that the rise of organization in the sense of evolution and life is kind of anti-entropic, like it disobeys the second law of thermodynamics or something like that. And Jeremy England's idea is that that in fact the rise of small-scale organized structures enhances the dissipation of heat or the dissipation of energy, which is the job of entropy. That's kind of one way to express what entropy is. It's causing energy which is originally kind of bound up in specialized places, whether that specialized place is all clumped together in the Big Bang or all the particles of air in one corner of the room, or something high in a gravitational field. And the second law of thermodynamics and the rise of entropy can be thought of as the universe's tendency to cause energy to spread out in the most spread out way that it can, so that energy occupies as evenly as possible, occupies all the possible states in which it can exist. And England's idea is that that complexity speeds up the global spreading out of energy. Okay, and I think that the example that we used in the episode was the idea of vortices in whether it's in a river or in cream that you pour into a coffee. okay, you see all these little structures, highly complex structures tend to arise, whether they're swirls of cream or little whirlpools in the river. And one of the roles of these is to speed up the way in which the energy can spread out, or the cream can spread out, okay, which is, I guess, a temperature differential. And so I don't know, I feel like probably a lot more work has been done since we did that episode on the actual physics of how these structures do, like the mechanism by which these structures cause cause energy to spread out. With vortices, you can kind of do it with fluid flow and some thermodynamics. With life, I feel like it's probably a lot more complicated. Like how do you prove that life is the natural way for entropy to do its work? It's kind of, by analogy, it's another way that the universe can become complex on small scales in order to become just more spread out and high entropy on large scales. So yeah.
Yeah, I just wanted to add, yeah, one of the first things that made me think of, I was just reading about it the other day, so missed that episode. It made me think of stars. They're very good at dissipating energy. Sometimes they explode and then condense and make new stars.
Yeah, totally. I've had the same thought. I think stars are like whirlpools. They're like little vortices, in that they're momentary local spikes or dips in entropy. But ultimately, what they do is they take what was once a cloud of gas, which is a concentration of energy compared to the surrounding void, and first they shine out that energy as radiation, and then as much more distributed particles in the supernova. And ultimately, if there's a black hole left, that black hole is going to Hawking radiate until it's nothing, and that is the highest entropy state that it could be. So totally. Real good thought. All right, what else we got?
I've been trying to mute myself to be better about that because I've got all kinds of children banging above me in the kitchen and stuff, but then I start talking and I'm not unmuted. Mac asks about the latest on Venus and if phosphine is in Venus's atmosphere.
Good
Who
question.
knows?
So I did hear that there was a potential hiccup in the interpretation, but I haven't looked in a while. So the observation was that there was an absorption line of phosphine in the atmosphere of Venus that was observed with two observations, two different radio telescopes. The second one seeming like a much stronger dip, and to the extent that it seemed really convincing. But I guess it's like a couple of weeks after we did that episode, someone told me that there was a question about whether, in fact, it was just a really unlucky confluence of noise so that there just happened to be this big dip exactly where phosphine should have been in both these observations, and I don't know how serious that was. Forbes has an article saying Venus is dead. New analysis shows phosphine is absent. God, sorry, you guys can Google this as well as I can, but I think there have been, so apparently there's at least one follow-up observation that doesn't find the strong phosphine dip, but I'm going to need to dig into this to see if this debunking is real or if we can debunk the debunking. Yeah, I don't usually go straight to Forbes.com for my science news. Although if Ethan Siegel is writing, then I do. But there's, yeah, have to get back to you. This one's dated in October, but I think it's just a single observation. So I think the answer is we're not sure yet. It seems that there hasn't been really extremely strong confirming evidence. There's been at least one observation that puts it in doubt. But yeah. All right.
Cam
I
says
was
too
really
much hype, then it all went quiet.
Yeah, exactly. I mean, because the astronomers are doing the work, and they'll, if it's real, then there'll be hype. There'll be yet more hype. But this is all just a couple of months ago. The astronomers have met. Believe me, this was big enough that observations have been made and people are working on the data, for sure. But this stuff's hard to do, and I think people are these days are really cautious about doing crazy press releases before they're sure, because it's just embarrassing if you.
Ever since the dust in the B modes thing, I think.
Yeah. I wasn't.
So how did it come out? Was there not a press release? Did the observations not get announced?
No, there was a press release because there were two observations. There was the first tentative one, and we heard nothing about that, rightfully. But then there was a follow-up one with ALMA, the Atacama Large Millimeter Array, and so that's a Chilean kind of millimeter range microwave facility, and that absorption feature to me looked like hugely strong, not noise. So I think it was totally justified. I really need to dig into this so-called debunking, because I'm not sure whether it was the fact that they think it's noise, or whether they think it's some kind of, I mean, there's all sorts of things. It could be like a feature in our atmosphere or something crazy like that. I mean, believe me, they go to extraordinary lengths to account for all of the known unknowns, but there are always potentially unknown unknowns. And so I imagine there are a lot of astronomers being very careful right now. I would expect more in the next few months, when these people are totally satisfied with their data.
There's also, of course, the question of, even if you have that real feature, what's the cause of the phosphine, which requires some modeling and so on.
Yes.
Yeah, I think there was a Stuff You Should Know episode where they revisited this. I think they were just saying, I don't remember the details, but they were saying, there's the existing data that could get reanalyzed with different methods, which made their conclusion maybe weaker. And then there are other people that tried to reanalyze the raw data that gave the signal, and they, under maybe slightly different assumptions or calibrations or something, again became weaker. So I don't know. I guess it's kind of a mix of the raw reanalysis of the raw data as well as the overall modeling that seemed to make people think it wasn't as strong a thing. But yeah, I'm really excited to see what follow-up measurements do. I mean, at some level there has to be an answer to this. This isn't like a quasar billions of light years away or something. This is next door. We should if we point good telescopes at it and so on, we should be able to nail it, I think. Although obviously the calibration and so on is hard.
Cam says, I think we're all used to getting answers really quickly these days, but science takes time.
Yeah. Good science.
You know what? When that was the thing that kind of amazed me about learning about LIGO and building, parallel detectors. And it's just like, because you could have a truck driving by one of the detectors and then you would have a signal,
Well, they also inject fake signals into that, and then they have like these double-blind tests so that the person on the detector on the day doesn't know if they're receiving a fake signal or a real one.
It's wild. You just have some jackass kind of tapping on it.
Yeah. On the glass, come to lunch. Yeah, you broke it.
Some jerk teenager.
Yeah. Well, there's there's gophers or something.
What is fuzzing, Brody?
Oh, yeah, injecting fake data and stuff, I think, right?
Oh, so it's like kind of software vandalism to screw with people?
I mean, it's like if you have a program that takes input, like you're typing stuff into it and you just put a bunch of garbage that's not stuff that come from your keyboard,
right?
Just raw data that is total garbage. and just randomly generate it for hours, days, and see if it breaks. And then how it breaks, and then you found a bug. And it could be a security bug. It could be important.
Is that standard process for like QAing development?
Not standard for most projects, standard for security related projects, yes.
Right.
At least ones that want to tout being secure.
Can I ask a question or read a question from Phil? I'm reading this one because it's for you, Eric. Okay, so wait on, sorry.
No, it's for Oliver.
Sorry, from Oliver. Yeah, I'm sorry, Phil, we can get to yours.
I'm like, don't read the one from Phil.
Yeah, this is for you. So question for Eric, and you don't need to answer it now, but you could. Patreon supports Spacetime with the cash that we can afford, allowing the show to go on. Indeed you do, and thank you. Is there anything that we can do to support Spacetime beyond this? We are all more than our money. We have skills, knowledge, and interests that could surely help run Spacetime better, organize some of the good work that's already been done, or just spread the word. Eric, what do you need?
This is such a generous question and offer, and it's something that I've chatted with Hank about before a little bit. And there are a lot of different kind of things that we could do. One of them that we've talked about is just trying to create a more searchable metadata tag database of all the episodes and the content, so that eventually we could have something to work with to create playlists and viewer checklists and means of kind of getting more precise results from the 250 something odd episodes that we produced. And so that's one thing that that we've thought tapping the community to kind of help us do, because to do it with any level of precision would take a lot of work and a lot of tagging and watching the episodes and thinking critically about what's there and then how to kind of identify it in a database. And then there's infinite other projects, and so that's something that I would want to think about. We do have a big project coming up next year that we haven't talked about publicly yet, but that we're going to really want to spread the word on to get out into the ether, to help get more support for it. And so that's something that I think we'll definitely be going to the audience and asking for help with, which is just helping to spread the word and spreading, getting it out to any contacts. It's not a podcast, but it is another production. It's another production project that it's really exciting and it's big, and we're going to need a lot of help with it. And so, the network of Spacetime viewers, I think, is really strong and large within the community that will be interested in this project. And I'm being very vague, but but it's coming, essentially, Oliver. We're going to make an ask of the audience, and so there will be a way. But that one particular project is something that the smaller piece of tagging all of the episodes to try to create a searchable database is something that I've spoken, with Hank about, and a lot of other people who watch the show and who think that would be a pretty cool thing to have, whether that eventually becomes something that lives on the web or in an app, but just like basically a better way to kind of mine the archive of episodes.
I actually just wanted to add, if since we have the scripts available in sort of a piecemeal way on the Patreon website, if there was some way of combining them into one document that could be searched for terms, that would also be helpful.
Yeah, Graham says there might be a machine learning kind of way to surface all that. Graham, are you volunteering?
I'm volunteering the idea. I mean, yeah, I'd have to think about what you want the specific, or what we want the specific input output kind of thing to be.
Right.
But there's definitely, semi-standard ways of applying a kind of question answer model to large corpuses of text.
Graham, could
Yeah,
you write a machine learning program to take all of the past scripts of space-time
And write new ones?
and write new ones? No, I was going to say turn them into a best-selling book, but
Oh yeah. Why have we not applied GPT-3 to this? Like we could just be generating scripts. Why have we not done a GPT-3 generated script and see if anyone
We could
notices?
GPT-3 the script, and then we could deep fake Matt.
Yeah.
Oh my, that would be fantastic.
We've been doing it for the past 3 years. No one's noticed.
Oh,
it.
sorry, yeah, I forgot about that. I wasn't meant. I was trying to double bluff, and you blew it.
Well, but I think Graham, like I asked Graham, I a couple months ago, or a month ago, I pulled every episode from YouTube and all the data, the viewership and the engagement levels and everything to kind of look at it all and do some like very hacky analysis on it, because we're doing, coming into 2021 and thinking about which episodes do the best, where audience interest is strongest and things like that. And Graham went through and helped me tag some of the quantum mechanics episodes in a little more fine-tuned detail. So we started thinking about that a little bit, but Hank and Graham, the idea of taking all the scripts and then putting them all, in a bucket and then saying surface, I guess, creating a big list of terms that people might be interested in, and then kind of figuring out a way to help people query it. Is that kind of the idea? We would kind of assign like, okay, here are the 40 or 50 terms that we want people to be able to look for within it, or?
Yeah, there's a few ways to think about it. You could sort of also look at it as a kind of an auto tagging problem, where we say we're going to have, okay, yeah, we could make everything searchable and do sort of near like fuzzy matching on terms and stuff like that. So you don't have to search for exactly a particular word, although keyword search is obviously super useful. We could also try and make something where you basically you take in a document, you classify, or it spits out, say, 5 tags that we've handcrafted for the existing episodes, and then future episodes it can auto tag those, and we can just check and see if they're reasonable, rather than having to do that manually, and also generate, basically tag it as topics, or even, not that this would be something we would actually do, but something like more abstract, like maybe difficulty level or something like that. Not that we would want to, label that, but yeah.
So guys, before this devolves into a workshop in which we actually build this tool, I think
Sorry.
I think we're now over an hour, so we should let people have their dinners or whichever meal they're up to, depending on location.
Okay. Well, anyway, thank you everybody for the great chat. Happy holidays.
Yeah. Merry whatever your favorite event of the season is. We'll see you all in a new and shinier year.
Yeah, hope you just have a really relaxing break, no matter what. And we'll see you in January for another one of these. Graham, apology accepted for the loud typing.
Yeah, classic Zoom rookie error.
Matt, enjoy your whiskey. Good night, Hank and Brody.
Thanks, guys.
See you later.
Thanks, everyone. Have a good
Thanks, everybody.
break.
All right. Happy New Year.
Good night.